what's the problem here? That was funny. So here's what it is. Let me explain my lovely drawing up here. So this is you, okay? And this is a cake on the counter.
Yes, I can get it.
Okay? Okay, so here's what we're thinking. Your grandma has made your favorite kind of cake, pie or dessert, or whatever it is that your grandma makes. I've never made it, lots of raisin, sour cream raisin pie, so whatever, okay? Here's the catch though. Okay, your grandma says, yeah, you can eat all the cake or pie or whatever she makes, but you can only cross the kitchen by taking steps that are half of the distance between you and the counter. Okay, so right now, you are 8 feet away. What's your first step? How far? 4 feet. So you're here. Oh. Okay, what's your next step?
2 feet.
2 feet.
4 feet, because it's still half the distance.
Nope, it's always half the distance from you to the counter. So this is you.
Oh.
On your second step, you have to go 2 feet, right? What's the next step?
1 foot. Grab
1
it.
foot.
The next step, it's in the curve.
And then half a foot. And then,
Corner.
and then,
8.
and then,
16.
and then, you'll never get there. You'll never get there. Will you ever
You don't have to use your arms. Just like use his arms.
No, but the deal was you can only make it if you take steps that are half the distance. So you can't eat the cake.
But I thought you.
Well, then the cake.
Why can't you just grab the cake?
I'll just eat the
No, okay, you're missing it at some point.
The point is, as the cake is.
Okay, I know it. But,
The grinding will never get you to it.
the distance, if you're only going to go half the distance in each way, are your toes ever going to be on the counter? No, you will never ever get there because you're only taking half and half and half. Half. So you're never ever going to get to the counter. You're going to get close to the counter. No, but the deal was that you kind of get to the counter. You never
Move the
get
counter
to
instead of touching this.
You're splitting hairs. Splitting hairs. Okay? Here's what I want to explain. Okay? The whole point of this was to show you that if you only go half the distance, you will never ever get there. Will you get close? Yeah, you'll get infinitely close because I can keep splitting half and half and half and half and half forever and ever.
I think definitely not.
Okay, but if mathematically, if I only went halfway each time, I'm not going to get there. Okay? So that's what we need to understand in order to figure out what we're talking about today. So we're graphing exponential functions. An exponential function is an equation where the base is a constant. So the base is just some number, like 6.
Are we going to do all today?
And the exponent is your variable. Independent variable. Remember, independent and dependent. Independent is usually the x. Okay? Exponential growth function is a type of exponential function in this form, where I just have something, some constant b to the x. I don't have anything added or subtracted. So, the whole point with the whole key thing was an asymptote. An asymptote is where the graph gets close and close and close and close and close and close and close, infinitely close, and will never ever get there. Okay, so it approaches but never reaches or crosses. If you were going to graph on your graphic calculator, an exponential, it will look something like this.
Nuts. Peanuts. And
How will bring it up?
We already.
Don't.
Wait, what?
What are we graphing?
I want you to graph y equals, we'll say 5 to x.
Wait, what is the
Wait, I don't know what's correct.
What's the
I know. Hold up. I'm gonna get to my
Right to the x.
How long does it take you to put all these, like, notes on the back side?
I'm gonna miss that. So I'm gonna miss it. Oh, I'm sorry.
Why? I'm looking at you.
Oh, yeah, that's right.
Dang it, why? I'm sorry. My husband is going to get passed over and fill in.
Well, you should just try that. Andrew.
I'm not going to drive 2 hours in the morning and 2 hours back.
Because you can't. It's funny because you're actually talking about this. My parents and Matt and I were like, oh, Mrs. Thompson is like the best math teacher ever. And my parents were like, I really hope she doesn't leave us alone because she gets a job or something like that. So
I'm sorry.
I had that too, actually.
we're never gonna be dumb and bad.
I know you're.
You were not going to be dumb in math.
We're all gonna be wrong.
You have Mr. Geary.
Or Mr. Anyway. Okay, so I've graphed. Now there's only go to the graphic calculator. I have graphed 5 to the x. So x is my exponent. Okay, I'm going to zoom in a little bit here. Notice that the graph gets closer and closer and closer and closer and closer and closer to the x-axis, but it's never, ever, ever going to cross it. It's never going to touch it. It's going to get infinitely close. Never. Never. Kind of like with the cake thing where I can just keep dividing by 2 forever and ever and ever off to infinity. That's what's happening here. Also,
That would have been cool.
notice that it's going to approach another asymptote here. It's going to go along here, then it's going to go up, and then it's going to go up and up and up. But it's going to have a vertical asymptote here where it's never going to cross over. Okay, see it right here? It's kind of like it's going to go almost vertical. It's never ever going to cross there. It's going to bump up against it, but it's never going to cross it.
So it's never going to cross the x or the y?
It crosses the y, but it will never cross the x. And in this case,
After.
it looks like about 2.5-ish is where our asymptote is. Okay, does this make sense? Alright. Let's go back here. Okay, so here's just up here a graph. Notice that it's going to get closer and closer here, but it's not going to touch the x-axis. It's going to go up and it's going to have a vertical asymptote somewhere around there. Okay? Alright, first one. They want us to graph the function and then state the domain and range. With these, it's just easier to make table values. Let's see. I can start with -3, -2, -1, 0, 1, 0.
Don't you only keep like 3 points?
Oh, we want to make a nice curve.
So if you thought 3 points.
I don't, you're not going to just go point, 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 and then somehow kind of graph it. Don't do that. No. You do that, I'm going to dock you.
Start with -1.
So I guess, okay, so here's the thing, Chandler. You can do that, but I'm going to count wrong. So it's your choice. Alright, let's go 3 to the -3.
I got it.
You got to 0. So your calculators can go out that far with decimal points.
They did 5 to the 100. Maybe that's correct.
So it's going to be, everybody knows how to find the exponent key on your calculator? It's going to be either a caret or it's going to be like an x to the y. When we are putting in negative exponents, you need to put them in parentheses, otherwise your calculator won't handle it. Okay, so I want you to go 3, and then here, your exponent key or whatever you have, and then -3 in parentheses and hit equals. Tell me what you get.
0.04. Yeah, that's what you're looking.
Yeah.
No.
So it's going to be a big one, decimal, we're around it too.
Mine isn't affected at all by
Isn't it? Are you sure you're hitting the right color?
yeah, that's these. Same exact thing.
Some calculators say it doesn't affect it. Alright, put in -2.
So anything to the 0 is 1.
So that's 1 repeating. So with this guy, it's 0.3333 repeating, right? Yeah, anything to the 0 power is always 1. That's true. How about 3 to the 1? That's easy. Is 3. 3 squared would get us 9, and 3 to the 3rd is. So if we were going to graph this, it gets kind of yucky. I would start at 0, 1.
Wait.
What?
Never mind.
where 1, 2, 3, 4, 5, 6, 7, 8, 9 goes off the graph. Oops, that wasn't very straight. Let's well, it's hard to graph those, but I want you to write them down. Yes.
Yes, that's it.
Okay, so then it asks us to state the domain and range. Okay, remember domain goes this way. Are there any x's that I cannot put in there?
No.
No, there's no restrictions. So the domain's going to be all reals. How about the range? Range goes this way. Are there any restrictions there? Will we agree?
Greater than 0.
Right. Well, it has to be greater than or equal to 0. Well, it can't equal 0. It has to be greater than 0 because our asymptote line is at 0. So y is going to be greater than 0 because it can't go below the x-axis. It can't equal 0 because that's our asymptote line where it will never cross it. All right, good so far?
Wait, so the range is always greater than 0. Yeah.
In this case, it's greater than 0 because we're at 0. It's our asymptote. Like if I took this and it was like somewhere over here-ish, then I kind of made a curve up there for a second. But if it was straight, then it would be 1, 2, 3, 4, 5 greater than a negative 6. Does that make sense?
Yeah, that makes sense.
Okay. All right, let's try example 2. Again, we're graphing. In this case, since it's a +1, I know that our graph is going to shift. I again would start with -3, -2, -3. So we're plugging in 2 to the -3 and then +1. So make sure you do your exponent first before you add the 1, not for order of operations. Yeah, you're probably going to watch it afterwards.
So we do that one.
Not unless you want to look at a table. So I have written down 1.125.
Yeah.
Better? Or was it?
And again, fill in a little gap here. All right, so where is there asymptote in this case?
Oh, I didn't think about it. Oh, it's gone.
Or y is 1. Yep. So again, if we're going to do domain and range, what'd you say for domain? All reals again.
Greater than or equal to. No, it's greater than 1.
Just greater than 1. So it can't equal 1 to the new term.
Oh, wait, okay. No.
Do you have it right through?
Can we see what?
I never really make it work over that way. Instead of to the x power.
I suppose you could. I don't think we're going to work with any of those, but I mean, they do exist. I'm not sure. We'll see. We're going to have that graph and graph and graph. Like you're saying, if I had. Oops. So you're saying like 5 to the square root of x? Is that what you're telling me?
Like having the 5 on the inside of the square root, and then the x root, and then have like a third.
Oh. You know, I'm sure they exist, but I'm not sure what they look like. unless you can try and graph it on yours. Mine is kind of a primitive graphing calculator over here, and I don't think it will do it.
There's something like that.
You can fiddle. I'm sure they exist, but I don't know what they're called. But I'm pretty sure they will have an access to it as well. Alright, let us move on. Okay, notice in this one, we have to watch our order of operations pretty carefully because we have exponents first. Before we do 5 to the whatever power, we have to take x minus, so we can figure out what that power is. Then take 5 to that power times the negative half. Does this make sense?
Yeah.
Order of operations. Okay, so again, I gotta start with -3.
Why don't you start with -1? Why don't you start with -1?
Could I just like to start with -3? That's just me. Okay, order of operations. So -3 minus 2 is a -5. So you're gonna go 5 to the -5 first, then take it times the -half. You have to put it in the right order, or it's not gonna work. Wait. Do that part first.
Oh, kind of weird.
Yeah, it is. It's like a -0.00016 is what I have written down.
I have 0.032.
I have 3.2. No, what she has is
I have 3.2 e minus 4.
Well, you're not.
I have the same technique. I like
Okay, go 5 to the -3. And then you forgot to multiply by a -half there.
Oh yeah.
Yeah.
Minus.
Times the -half. Okay, so if we go -1/2, 5 to the -2 minus a 2 would be a -4. So this is a -0.0008.
My calculator, when I do this, if I go 5, and then -5, comes up with like 3.2 to the -0.4.
It's because your calculator's not giving you all those decimal places.
Yes.
So you're like,
It's saying move the decimal place 4 times.
there is that
0, 0, 0, 2.
so then divide times
Then you're gonna move it.
How would I want to my 4? Here it is.
All right. So if we keep going in our table.
So this started out like,
Okay, stay with me. Alright, if we're going to try and graph this thing, it's kind of yucky. I would start graphing with the 2, -2.5.
oh
kind of
no,
like
this
there.
is not.
So this is way down here. This one's almost.
Oops, I missed.
So it's going to go, where's our asymptote in this case?
Zero.
Yep.
Why equals 0?
Oh no.
It's pretty close.
Okay, so domain is all reals. Okay, what's our range? Y is what?
Less than.
Less than
0.
0. So we'll never get to 0. Okay, close to 0.
What's Friday on Thursday?
I did Thursday. Yep.
Oh,
Alright, I have a typo. Let's see, right here. Change this, guys. This is a typo. This should say 1 plus R.
That's what it says. Sorry.
Oh, I did change it on first? Okay. Good. Alright, so we're going to use the real-world application of these exponential functions. Usually it's used to model population growth or decay. In this case, we're talking about growth. Using this formula, where A of t is the amount in the population, the total amount, after T time periods, however many times we're going to gather the information, like every year, every 4 years, every 8 years, whatever. A is the initial amount where we start with the population, and R is the percent of increase per time period. So the base of this exponential function, what we're taking to the exponent, 1 plus R, is called the growth factor, or excuse me, the growth rate. Growth rate.
Why is your example different?
My example is different than yours. I forget what yours says, but it's not this.
It's the first one says this one.
I changed it.
Why don't you change it? I just make notes on there.
Why did I change it?
Why did I?
What? Because either notes my hardware thing is from last year. Yes, I just didn't change it.
It's all.
Urban dictionary. All right. Here's what it should be. So the first year census was conducted in 1790, and the time the population was. Since the U.S. population has grown by approximately 2.03% annually, draw graphs from the population growth of the U.S. since 1790. Okay, so we're going to have to plug into our formula this A of T. All right, so we have to figure out what piece goes where. Okay, so A of T. We don't have anything to plug in for that guy. A is where we start. What's our population when they started this? Okay, we're going to take it times 1 plus the growth rate, or excuse me, the percent of increase.
It's 0.0. What do you have 1T? Oh, 1 plus.
1 plus. So we can just put these together and say 1.0203 to the.
I said 1. Oh.
So I put this together. So it's just, we're just leave it as a T right now.
We'll use X.
No, because it's a T. Because it's A of T, not A of X. So it's an A of T. Because T is T. Alright, so since we're trying to model the population growth since 1790 as a basis to start our table at -3.
No.
No. Okay, what, John?
Not borrow your calculator.
No. From right this very second you may. As long as you tell me what to write down. Okay, my exponent key on this one is this one. You have to put negatives after the number if it's a negative number. All right, so where should we probably start with our T's? Okay, well it says since 1990. It's going to be our T, right?
Right now it's 2013.
It is 2013 now. How many years has it been since 1990 or 1790? Excuse me. A long time. 223. Okay. So, what do you think? Where should we probably start? What makes sense? Go by 50s, maybe? By 20s? By 2s? That's
Wait, we're only supposed to be finding 50s.
by 50s?
You can do it by 2, so.
Why do you go back?
We're not by 1 reach.
Go by 2s because you can never. Since 1790,
How did I go up by 1790?
because it says show the population growth since 1790.
But it's obviously going to go like what our other files were like, so we don't see it go all the way down there.
But it says since, so we have to start at 1790. Since then, yeah. So let's go by 50s.
We're going to go above it.
Yeah, sure. All right, so stay with me. Stay with me. Do you want to go by 30 or is it good? It's just paper. No, it's more. really quick change it. So tell me, if we plug in 50, what's our population?
A big number.
Well, give me that big number.
107.
107.
324.
324.
78.
70. Okay, tell me that's enough. That's enough.
121.
And we'll go with that. All right, how about if we put it on the screen?
It's gonna be bigger.
That is even bigger.
Um, 2931.
2931.
5300. Oh, I got
That
that answer.
Okay, why is this answer smaller than this? No, it's not. I'm sorry. I was looking at the weird. It's not. We're good. I was looking at
Doing that.
That's right.
Oh, that's a pain in the butt.
Do that.
Okay, the next one.
All right.
8007
8007.
3475.
Okay.
Yeah, I got that.
Next one is 2187.
2187.
We're just rounding.
7.
Sorry.
Yes, we got 8.6 people.
Oh yeah. No, but we round up.
Say again.
Oh, it's round down.
Oh, you have 87.
Okay, 8717 238.
238.
The next one's 17238.
Why is 150 smaller?
No, it's not. It's 80 compared to 29.
Oh,
Okay, 21.
Just start at the beginning. So obviously I'm not.
That's what I'm gonna do.
2187.
87 17 283.
283. All right.
I mean 28. Yeah, yeah.
Okay.
238.
Great.
That's alright. I'm going crazy.
Okay, one more.
Okay. 59 74 16 16 2.
All right. All right. So if we're starting, stay with me, guys. I'm going to give you more homework. You're not paying attention. So we're starting our graph where x is our time. The x is our time. We're starting at 1790. If we're going to go 50 years since then, what year is that? 1840. So I'm going to go 2, 3, 4, 5. So 1840. Okay, so another 50 years since then is going to be at 1890. And then another 50 years would be
This book was probably made in 1990.
I'm sure it was.
Yeah, see? So then they gave us enough room.
we would live in 24 yet.
True. But did we go there? Let's see, we said 50, 100, 150, yeah. So we're just, extrapolating.
You know, even if we went by 10 millions, it still wouldn't reach what we need.
Okay, well, let's break it graph. We don't have to start at 0, do we? We can break it. Where should we probably start?
100 million.
100 million?
To reach 5
10 million, that's where we need to start.
That's where we need to start. No.
10 million.
That's
Sure, we can start at 10 million. So,
So you guys are around 500 million. You're 50
We can't go by 150 minutes.
I know, when you go by hundreds, like they said.
Because you need to get to 500 minutes, so that's not gonna get there by time.
no. So, like, is this
Should go by
Is
hundreds.
this accurate? I mean, is it a good
Not at all.
formula?
No. So we should be going.
Yeah.
Yes.
I just thought it was kind of weird. I don't know. We need to have a serious
All right. So we can grab what we got anyway here. Already?
Contact.
You're on top of me.
That's all horrible.
Technically, it's started sooner because of the strong line.
Yeah, okay. True. Yeah.
I'm dying.
You guys get the idea. I'm just worried about that you know how to write the formula and you can find the answer.
That's all horrible.
It is a horrible graph. I agree. Okay, going on. Going on. So, exponential growth. Stay with me, please. Exponential growth, decay, goes up this way, or we could go down this way. Decay is going to go down like this. Okay, so we're going to start at the top and go down to an asymptote here. With the growth, we'll start at the asymptote and go up or down. With the decay, we're starting above and going towards the asymptote. Does this make sense? All right. Again, we're graphing the functions. So I would start at -3.
Is this the same thing?
Yep, it's the same idea. It's just gonna notice that we have a fraction as our base. That's gonna change the shape of our graph. We're gonna start at the high number, go down towards the asymptote.
Oh my goodness.
So we should have 27, right? Because with the negative exponent, remember that means put the fraction, so we're really doing 3 to the third, which is 7, right? So then if we flip it again, what's 3 squared? 9, and then 3 to the 1 is 3. And then the 0 power is 1. Now we're saying, if we want to flip, we could say 3 to the -1, so that's going to be, yep, a third, yep. And 1, 1, 1 again. It's not a
It
parabola.
can't be a parabola.
It's not a parabola, actually, don't.
It's impossible.
Good job.
No, it's not possible.
It's not, it's impossible to use equations.
When we're looking at these children, it's not a parabola. When we have an x as the exponent, it's never a parabola. Never. You find
You
something
still-
with x with an exponent, it's a parabola.
You would spend your life trying to find a parabola in this equation, and
No, which I do if I did.
Not gonna waste.
Crazy. Those people could be there.
All right, do we need to grab one more? Or are you guys get the idea? All right, on B. Stay with me for a second.
Get all
Stay with me.
that.
On B, tell me, order of operation wise, what are you going to do first?
Wait, we're not doing this one.
I know, I'm just saying, if we were going to do it, what would you do first?
The exponent.
Okay, you'd add to the exponent, yep. And then you would take the 1/4 to whatever that power is, then what would you do?
Times it and then minus it.
Yep, multiply by 2 and then subtract. a,
You put a fraction in.
how do you put a fraction in that calculator? You can't do it.
Okay.
I mean, you can say parentheses 1 divided by 4, close parentheses or something.
All right.
But you can't, like, there's no function to do the fraction. All right, you're all reading the book.
Because our. I know. Taylor, are you gonna have fun drawing today?
That's not what